Hi guys, welcome to this lecture on electrostatic field. The forces present for static charges are called electrostatic forces. It is conservative and therefore we can introduce the concept of potential energy. In this short lecture, I will introduce the work done in moving a point charge, electric potential, and electric potential energy. Let's start. And this is the outline of this lecture. Let's start with this scenario. Given a charge Q in an electric field E, located between two charge plates is shown in my drawing. This electric field exerts a force on the charge with the expression F is equal to QE. To maintain the charge in equilibrium, a force must be applied in opposition of this. And therefore, we have this expression F sub A is equal to negative QE. Note that both of these forces are shown in my drawing. Remember that work is defined as a force acting over a distance. If this charge is moved with an infinitesimal displacement ds, a differential amount of work dW is done by the applied force F sub A. And this can be expressed as follows. So we have dW is equal to F dot ds, or this is also equal to negative Q E dot ds. Note that when Q is positive and ds is in the direction of the electric field, dW is less than 0 or negative. This indicates that work was done by the electric field. Similar with gravitational field, moving a positive mass from higher to lower elevation. If dW is positive, it means work done against the electric field. The work done is just the gain in potential energy when charge is displaced from point A to point B. And we have this expression for our potential energy. So we have delta U, or this is the gain in the potential energy, is equal to UA minus UB, or this is equal to this integral. We can define now the electric potential V, which is equal to the electric potential energy U over charge Q. And therefore, we have this unit for our electric potential. So this is joules per coulomb, or J over C. The change in electric potential between 2 points, let's say point A and B, is expressed as follows. So we have delta V is equal to V sub A minus V sub B, or the electric potential at this point A and then point B, and this is equal to the negative integral dA of your electric field dot with your ds, or displacement. Note also that the gain, or the change in the potential energy, is equal to Q, your charge, times the change in the electric potential delta V. This one, given that this is just the change in electric potential, it has a unit of joules per coulomb also, but we can express this one as 1 volt. So 1 volt is equal to 1 joule per coulomb. This is also known as the voltage, and this is the popular term for this, or it's also known as the potential difference. Let us define again an electric potential. This is a quantity associated with spatial points around a single charge. Let us say we have this positive charge Q located at a point in space. We can define an electric potential due to the presence of this single point charge in space. Let us say a distance r sub 1. The electric potential is, let's say, about 50 joules per coulomb. Note that the units is joules per coulomb. If we have a distance r2, which is near the point charge, we can expect a larger value of electric potential, let's say about 350 joules per coulomb. If we place a charge at those given locations, we will have an electric potential energy, U. So that's U is equal to QV with the units of joules. And for example, we have this one. So U sub 1 is equal to 50 joules. Last, voltage. Voltage is different but related to electric potential because voltage is the electric potential difference at 2 points. it has a unit of joules per coulomb, but we can also define it as volt. And for this case, if we are getting the potential difference at point 2 and point 1, so V sub 2 minus V sub 1, we have 300 volts. Given our expression for the potential difference as this negative integral, when we express the infinitesimal length ds along the x-axis only, we have this electric field expression along the x-axis. So we have E sub x is equal to negative dV over dx. For the case of constant electric field, for example, a parallel charge plate, the potential difference between 2 points with distance x is just delta V is equal to E, the electric field, which is a constant, times x, which is the distance. If the potential is 0, let's say at x is equal to 0, then the electric potential is just E times x, as shown here. So V is equal to E times x. And the potential energy of the charge Q is just Q times E times x. And therefore, we can also define this one as Q times V, wherein your V is your electric potential. It has an analogy with gravitational potential energy, where Q is like the mass, m, and electric potential V is like g, your gravitational acceleration due to gravity constant, times y. And this is proportional to a certain distance x or y. When talking about charged particles, let's say protons or electrons, we use this unit of energy, which is electronvolt or EV. If a charge Q is placed through a potential difference, let's say delta V, as shown in the drawing. So we have this point charge Q, then we have this delta V. Its potential energy changes by this. So your delta U, or the change in the potential energy, is equal to Q times the change in the electric potential. When this charge Q has an amount of charge E, which is equal to about 1.602 times 10 to the negative 19 coulomb, and this charge falls through 1 volt, its potential energy changes by 1 electron volt. So your 1 electron volt shown here. So we have this one. 1 electron volt is equal to E times this change in potential, in the electric potential, and this is equal to about 1.602 times 10 to the negative 19 joule. I have this diagram showing the electric field lines in black arrows going into the electron, given that the electron is an electric field sink, and equipotential contours shown in red circles around an electron. This path, the circles, is called equipotential line, or equipotential surface, or volume, wherein the V, the electric potential, is constant. If a charged particle traverses perpendicular to the electric field lines, no work is done on it, and the electric potential energy, the delta U, does not change, or this is equal to 0. Now, the work done in moving a certain point charge, let's say from point B in space to point A in space, in a given static electric field, is independent of the path taken. It is shown that the line integral for path 1 is equal to the line integral for path 2. We have this negative sign here. Therefore, we define a closed contour integral form by path 1 and path 2 equal to 0. Note that dl here is just the same infinitesimal length ds we have defined previously. Given this property over every closed contour, the value of any line integral of this conservative field, so we call this one your electric field, a conservative field, is defined solely by the path endpoints only. The choice of any path between 2 points does not change the value of the line integral. So, we have defined electric potential and potential energy already. Let us discuss the expression for electric potential between 2 points. We can define the potential difference or the potential at point A with respect to point B uh, as the work done to move a unit positive charge Q or capital Q from point B to A. And this can be also expressed as this integral. So this is equal to negative integral AB of your electric field dot with this infinitesimal length dl. The reference point here is placed at the lower limit of the integral, and the negative sign is due to the applied force we have discussed previously to make this charge in equilibrium. Given that the electric field is a conservative field, as we have mentioned before, we can also write the potential difference between points A and B as follows. So we have this C as our reference point. So this is equal to VAC minus VBC. We know from our discussion of electric field that a point charge Q will emit electric field radially as shown here in my drawing. Thus, we can express the infinitesimal length dl here in terms of the radial distance dr. And therefore, we have this form. Knowing the expression for the electric field E sub r, the one we have placed here, we now have this form. So this is equal to negative q over 4 pi epsilon naught times this quantity that you will get after you evaluate this integral. If our reference point B is moved out to infinity, so if your r sub B approaches infinity, then we can express the potential of a point charge as follows. So we have V is equal to Q over 4 pi epsilon naught 1 over R. And this is quite similar with our electric field expression, except that this is just R, not R squared. And if we have a collection of n point charges, this can be expressed as a summation as shown here. In summary, we have shown a differential amount of work dW for a charge that is moved with an infinitesimal displacement. We have differentiate electric potential, potential energy, and voltage. We have said that no work is done for a charged particle moving on an equipotential line. Electric field is a conservative field, thus it is path independent. Last, electric potentials between 2 points and a point charge were introduced in this lecture. And that's it. Thank you. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.